we were talking about displacements and bending angle in the last lecture. Today also we'll do one example and we'll try to calculate in this case. So this is an example which we will do today, and we will try to calculate maximum displacements. So there is at some point you're gonna get maximum displacements because of this load, and this is what we will calculate. So in this chapter, we'll talk about three different methods to calculate the bending angle and the displacements. So one method which we explored last time is called equation method. We'll also use equation method today, and we will also use another method which is called graphical method. So graphical method is also a way where you don't have to formulate equations. You can just directly draw shear force and bending moment diagrams and bending angle and displacements by just looking at the simply supported beam with some loading condition, and you can just directly figure out the shear force, bending moment diagrams, and the bending angle and the displacement diagrams. But you cannot know everything, so in order to know everything you need the equation method. So first we'll try to solve this simply supported beam with the equation method, and we will verify this all the shear force bending moment diagrams by the graphical method as well. And next time we will explore superimposition method. So what we have to do in this simply supported beam is that we have to calculate reactions first, then we have to cut a section, we have to expose internal loads, and we can formulate the equation for shear forces and bending moments, and we can also formulate the equations for the bending angle and the displacements. And once we have all those equations, then we can simply plot and we can draw shear force diagram, we can draw bending moment diagrams, bending angle diagrams, and we can also draw the displacement diagrams. And from those diagrams we can figure out where we are getting the maximum displacements, and that's gonna be the answer for this question. So we already know the process, we already know the steps, so I'm just gonna start working on this example. So everybody can calculate the reactions, right? So you have to use equilibrium equations, and once you use the equilibrium equations, you're gonna get the reactions. So I'm just gonna write down the reactions for you guys. So if you try to draw the reactions, this is what you're gonna get. You're gonna get 2 kilonewton and you're gonna get 4 kilonewton. And you can calculate these reactions by using equilibrium equations. So in this example, what we are doing is that we want to calculate the maximum displacements in this case. And also we will draw shear force, bending moment diagram, bending angle diagrams, and the diagram for the displacements. So in order to formulate equations, we have to cut sections, right? So in this case, we have to make two cuts because you have a load, and there's gonna be a cut before the load and there's gonna be a cut after the load. So I'm gonna make two cuts and I'm gonna draw here. This is gonna be cut 1. This is gonna be cut 2. Cut 1 is applicable from 0 to 2 meters, right? Cut 2 is gonna be applicable from 2 meter to 3 meter. So this is the cut here. This is the cut here. We already know the load, which is 2 kilonewton. And we also know the external load, which is 6 kilonewton. So we are formulating the equations. So it's an equation method. So we're gonna call x till the cut. This distance is 2 meter, and this distance is x minus 2. And we have internal shear force and bending moment, which we are interested in. So we have shear force and bending moment. We have shear force and bending moment. So we already know how we can formulate the equation. So we're going to use equilibrium equations and we'll calculate V and M for both the cases. So if you do the equilibrium equations, I'm just going to write down the final answers. So the answer for V in this case would be 2. And in this case, it's going to be 2 minus 6 minus V is equal to 0. So in this case, V is going to be minus 4. And moment also you can calculate. You're going to get 2x as an answer. And here you're going to get the moment as 12 minus 4x. So now we can also calculate bending angle and the displacement. We know the bending angle is 1 over EI integration of the moment dx. We already have the moment, so we can calculate the bending angle. Similarly, we can calculate the displacements also, which is integration of the bending angle. So you can use these two equations and you can also determine the deformations in terms of bending angle and in terms of the total displacements. So we did this in the last example. So I'm just gonna write the final equation for the bending angle. So the equation for the bending angle is 1 over EI x squared plus C1. And the equation for the displacement would be 1 over EI x cubed by 3 plus C1x plus C2. Similarly, from these two equations, we can also determine bending angle and displacement for the other part. So let's call this bending angle theta 1, this V1, and for the cut 2, I'm going to call it theta 2, which is equal to 1 over EI (12x minus 2x squared plus C3). And the displacement would be equal to 1 over EI (6x squared minus 2x cubed by 3 plus C3x plus C4. So that's all what we need to draw shear force. So from these equations, we can calculate shear force diagram. From here, we can draw bending moment diagrams. From here, we can draw the diagram for the bending angle. And from these equations, we can draw the displacements diagram. But in this case, first we need to calculate the C1, C2, C3, C4. So once we have those C1, C2, C3, C4, then we are good to go. We can just draw the diagram directly. So we have 4 unknowns, C1, C2, C3, C4. So we need 4 equations. So last time we used boundary conditions to figure out these equations. Now also we're going to use boundary conditions and other conditions to figure out those 4 equations. And then we can calculate the C1, C2, C3, C4. Once we have those, then we have all the equations we need to draw any diagram which is required. So let's figure out the boundary conditions. So I'm going to draw a simply supported beam. We have a load which is 6 kilonewton. If someone has any questions regarding the integration, then they can let me know. But you have shear force, you integrate it, you get 2x. You integrate a moment, this which is 2x is gonna get x squared by 2, so it's gonna cancel out plus constant. If you integrate this, it's x squared, so you're gonna get x cubed by 3. You have c1, you're gonna get c1x, and then you get another constant. So that's how you do the integration. We have reaction which is 2 kilonewton, and here we have reaction which is 4 kilonewton. This distance is 2 meters, this distance is 1 meter. So the boundary conditions are actually the values of bending angle and displacement which we already know. So if we already know something about these equations, then we can input those values and then we can calculate C1, C2, C3, C4. So we know this is a pin support. So at the start, our x is equal to 0, right? So at the start, we have no displacement. We already know this because it's a pin support, and at the constraints, you're not going to get the displacements. So if x is equal to 0, displacement is equal to 0. So if you put 0 here, if you put x is equal to 0, you're going to get displacement 0. We also know that at a roller support, where x is equal to 3, our displacement is 0. So we also know displacement is 0 here as well. So you have two equations now, right? So let's try to draw the displacements of this simply supported beam. So if there is a load at the top and it's pushing the simply supported beam down, so you can imagine what a displacement curve would look like. So this beam will bend something like that, right? Because of this load, the beam will bend. So I'm gonna draw this elastic curve. So it's gonna be something like that. So this is an elastic curve, an actual bending of simply supported beam under this load. So this is elastic curve. This is our elastic curve. So your equation, I'm going to call this equation A. This equation I'm going to call B. This equation I'm going to call C. This equation I'm going to call D. So at this point, before this point, from here to here, these two equations are applicable, right? After this point, from here to here, these two equations are applicable. So if you want to calculate something in this region, you're going to use these two equations. If you want to calculate something in this region, you're going to use this equation, right? But at this particular point, you can use any of these two equations, right? These two equations are basically equal. So at this particular point, theta 1 is equal to theta 2, and displacement 1 is equal to displacement 2. This is at x is equal to 2. So if you put 2 here instead of x, and also if you insert the value x and replace it with 2, then theta 1 is going to be exactly the same as theta 2. Similarly, displacements are also going to be the same here. So you have two boundary conditions, this one and this one. These are called boundary conditions, right? So because these two equations are coming from boundary conditions, and this is called continuity condition. So basically we need these conditions to calculate C1, C2, C3, C4. So I'm going to use these boundary conditions here. So if I use x is equal to 0, I get displacement is equal to 0. So from B, 0, 1 over EI 0 cubed by 3 plus C1 0 plus C2. And if I use boundary condition here from equation D, I'm gonna get 0 when I put 3 instead of x. So from here you can calculate C2. From here we'll see how we can calculate C1 and C2. And also we have continuity equations. So I'm going to write continuity equations also here, which is theta 1 is equal to theta 2. So at x is equal to 2, theta 1 is equal to theta 2. And at x is equal to 2, displacement 1 is equal to displacement 2. So you guys think you can calculate C1, C2, C3, C4 from these conditions. So you guys can try to calculate and let me know what are the answers for C1, C2, C3, C4. Your final equations. So C1 is uh, C1 is minus 8 by 3. Or I can just write down below. So I'm going to write down the final equation. This is C1, right? Or let's just write it here. This is minus 8 by 3, which is C1. So C1 is minus 8 by 3 and C2 is 0, right? And C3 is minus 44 by 3. And C4 is 8. So that's the final equation. So we have all the equations we need. So we have the equation for shear force, we have the equation for bending moment, we have the equation for bending angle, and we have the equation for the displacements. So we can draw the shear force diagram, bending moment diagram, bending angle diagram, and the displacement diagram, right? So you put x is equal to 0 here, and then x is equal to 1 or 0.5 or 1, 1.5 till 2, and from here 2 to 3, you're going to use these equations. So we can use the equations to draw shear force bending moment diagrams, which is, I mean, you guys already know how to do it. So we're going to use a graphical method to do the similar thing. So some of you guys may already know how to do the graphical methods, but those who don't know, I'm just going to draw in front of you guys like how it looks like. So let's draw our simply supported beam. So this is our load, which is 6 kilonewton. We already know the reactions, which is 2 kilonewton at one support and 4 kilonewton at another support. And this distance is 2 meter. This distance is 1 meter. So the first step is to calculate the shear force diagram, right? So the easier way is to just use the equations and draw shear force diagram from the equations. But I'm gonna use a graphical method, which is drawing the shear force from the simply supported beam by looking at the loading conditions and the reactions. So we know reaction is 2 kilonewton, right? So this reaction is actually a shear force. If you cut a section, this is what you're gonna get the shear force. So reaction is actually a shear force. So I'm just gonna draw this reaction as a point in shear force. So this reaction I have, this is 2, so I went to uh, that same magnitude. From here to here, there is no external load being applied. So this shear force is going to remain the same too. There is no load till point here, so the value is going to remain the same. Now there is a shear force which is pushing down. So I have to subtract this with this. So this was 2 upward. So I have 2 force kilonewton upward, and then you have 6 down. So I'm going to go down 6. So 2 here, it's 2 minus 6, which is minus 4. And then you have no loads, so you're going to go straight, and then you have 4 kilonewton force upward, so you're going to go 4 up from here. So this is straight, and then you have 4, right? So negative 4 plus 4 is going to be 0, so you go back to 0. So that's how you can also figure out the shear force diagram just from the loads. So this is positive, this is negative. So that's how what we did. Like we have the external load and we have the reaction load. This is 2, so shear force is 2. Nothing happened. You have a force which is acting downward 6, so I'm going to subtract 6 with 2. It's going to go down, and then there is nothing, so straight line, and then there is 4 Newton force up, so we go up. So that's how also you can draw shear force diagram, which is basically an integration of this loading condition. So yeah, and from shear force, we can draw from the shear force, we can draw bending moment diagram as well. We can also use the equation, but we can also use the integration of shear force. So what we're going to do is that we're going to integrate the shear force and we'll calculate the bending moment diagram from the shear force directly. So now we'll draw bending moment diagram. So the integration of shear force is bending moment, right? So we're gonna integrate. What is integration? Integration is basically area under the curve. So you take area at any given point, and that point is gonna be a bending moment. For example, if you want to calculate bending moment at distance 1 meter, if you want to calculate bending moment at this point, then we can calculate the area till that point, and we're going to get the bending moment value. So we also know it's a simply supported beam, so we also know the boundary condition. We also know the bending moment is 0 in the start, and the bending moment is 0. So you have simply supported beams, so at a pin connection and at a roller connection, the bending moment is 0. So you're going to start from the 0 value. So if you want to calculate what value should be here, what is the value here, you can calculate the area before this point, all this area. So if you calculate entire area, that's going to give you this point. So let's try to calculate this area. This distance is 1 and this is 2. So the area is 2 into 1, 2. So this is our answer for this. If I want to calculate this point, then I have to calculate the entire area of the shear force. So this entire area is actually, this entire thing is 2 and 2. So it's going to be 4. So I have 4 value. So I'm going to draw a line, and that's how we can calculate the bending moment diagram from the shear force as well. You can also use equations. So it is positive. Now this area is negative. So before it was positive shear force, so I was adding the areas, right? So now you have a negative area. So I'm going to subtract this entire area. So if I want to calculate a point here, so you already have area 4, right? So I'm going to subtract this entire area. So if you calculate area for this negative region is going to be 4. So 4 minus this 4 is going to give you 0 value. So I'm going to join the points, and this is our bending moment diagram. And this is above, so it's all positive. So we can also calculate the bending moment diagram from the shear force by just integrating, which is calculating the area under the curve. So if you want to calculate at any point, if you want to calculate at this point, what would be the value of the bending moment? So you go up and you calculate area beyond this point, entire point, and that area would give you the value of the bending moment. Does it make sense? Okay. So now we can move to bending angles. So now we're going to draw a bending angle. So let's draw the bending angles. The best way to draw bending angles is use this equation, right? So everybody understand how they can draw a bending diagram from this equations, from this equation and this equation, right? Okay. So now we're gonna try to draw it without using equation, but bending angle and the displacements are a bit hard to calculate because we don't know. For example, in bending angle, we don't know the value in the start. So I'm gonna draw this simply supported beam here. This is a load, right? So if you try to draw the elastic curve for this point would be something like this, right? So there is some bending angle in the start, so it's not 0. There is also some bending angle in the start at the end also, so it's not 0, right? So there is some bending angle. So this is clockwise bending angle, so I'm going to put 0. This is anti-clockwise, so it's positive. So we have some negative bending angle in the start and some positive bending angle in the end, right? Because it's a simply supported beam, so the bending angle is not 0. But if you want to draw the displacement diagrams, we know that the displacement is 0 at the start and the displacement is 0 at the end. So you need to know the boundary conditions to draw the diagrams. So for moment, we already knew that moment is 0 in the start and moment is 0 at the end. For bending angle, we know it's not 0. It's some negative value in the start and some positive value at the end. Displacements, we already know it's 0 and the 0. And once we know the boundary condition, which are the constants, then we can integrate the bending moment diagram to calculate the bending angle. And once we have the bending angle, we can integrate to calculate the displacement. And integration is nothing but the area under the curve. So if you want to calculate the bending angle at this point, it's going to be at this point is going to be this area plus whatever we have in the start. So if we start from here, uh, and if I want to calculate, so this is going to keep on increasing till this point. So if I try to draw, this is smaller area, this is larger area. So this is smaller area, so it's going to start from the straight line something. This is also smaller area, so it's going to start something from straight. And this is larger areas, so it's going to be something like this. So it's a straight line. So if you integrate straight line, you're going to get a curve, cubic. So you can also integrate this whole thing. This is negative. And this is positive. And if you integrate this entire thing, this is negative, so it's gonna go down, right, till this point. And then it's positive after, so it's gonna start to go up. And at this point where bending angle is 0, you're gonna get the maximum displacement at bending angle is equal to 0. But we don't know this distance. So drawing bending angle and displacements are a bit difficult. I would say bending angle is difficult. Displacement is still easy. We already know the displacements are 0, and we already know how it's gonna bend and what is the elastic curve. But you can draw shear force diagram and bending moment diagrams directly also. But what we will do is that we can figure out this point if we want to figure out. This point we can figure out from this equation, right? So if x is equal to 0 at this point, you can calculate theta 1 from this equation. Let's call this equation 1, this equation 2, let's call this equation 3, let's call this equation. So what I want you guys to do is like calculate and give me this value. So give me this value, which is gonna be equation 3, I guess. So these are the equations. You can write them down. This is equation 1. This is not equation 3. So give me this. So everybody has written. So you have these equations. Everybody has written these equations. You guys can write these equations. So you have these equations. Now give me this value. So whoever this. So calculate this value and also calculate this value. So everyone can try to calculate this point. They can also try to calculate this point from equation. They can also try to calculate this distance x, and this distance x is same as distance x, and then we can also calculate this V max. This you will use equation 1. This you will use equation 3. And this one you will use, I guess, equation 1. And this you will use equation 2. So here you have to put x is equal to 0, and then you will get the value of theta. Here you have to put x is equal to 3, you get theta 2. And here you have to put theta is 1 is equal to 0, and then you will get the value x from equation 1. And then you can use